So welcome everybody to this MaLGa seminar, which is part also of the Ellis Genoa activities. So today we have Giulia Luise from the Imperial College, which will give us a talk about regularity properties of entropic optimal transport in applications to machine learning, and just a brief bio. So Giulia has recently obtained a PhD in machine learning at UCL under the supervision of Ciliberto and Pontil, and now is a research associate in the Imperial College, where she started working on some reinforcement learning. So please welcome Giulia.
Yep. Hi, everyone. Thank you very much for inviting me to these MaLGa seminars. I'm going to talk about some of the work that I did during my PhD at UCL. And so this is joint work with Carlo Ciliberto, Saverio Salzo, also from Genova, Alessandro Rudi, and Massimiliano Pontil. And I'm going to talk about regularity properties of entropic optimal transport in applications to machine learning. So the talk is divided into three parts. The first part is a soft intro to optimal transport. The second part is a less soft introduction to the advantages of using entropic regularization in terms of regularity itself, and we're going to see in which sense. And the third part is about applications of such regularity in machine learning problems. So comparing probability measures is of fundamental importance in many machine learning problems. And to do so, there are many ways. Like one can use several distances and several divergences to compare distributions. Well-known examples of such divergences are total variation or Kullback-Leibler, other F divergences, and also optimal transport. That is in some sense a special one. And entropic optimal transport, which is what I mentioned in the title, is a regularized version of optimal transport with more amenable properties that we're going to see later. Now, we say optimal transport is a sort of a special one for a couple of reasons. And the main one is that optimal transport distances faithfully incorporates the notion of geometry that we have on the space that we are working on. And these geometric properties have a deep impact in what is considered close and what is considered far under OT metrics, in comparison, for example, to what happens with Kullback-Leibler or other F divergences. And so just to give a more concrete example here, assume we have these three images, and the one in the middle is our target. Then intuitively, we would say that the one on the left is a way better approximation of such target than the one on the right, that is very blurred and very dark. However, if we use Kullback-Leibler to compare the corresponding histograms, what happens is that our intuition is not actually reflected. And using Kullback-Leibler, the histogram related to the very dark image is actually closer to the histogram of our target than the one on the left. On the other hand, if we use optimal transport, our intuition is respected, and we have that the histogram associated to the image on the left is indeed closer to the histogram of our target. So this is just to give a sort of flavor of how optimal transport distances differ from KL and similar other divergences. To proceed with the presentation, we need some notation now, and also the main definitions that we are going to use in the rest of the talk. So in the following, I will denote by X compact subspace of a Euclidean space, RD. M of X will be a space of finite measure over our domain. P of X is the space of probability measures. And then we are going to use cost function C that is continuous and symmetric. And you can just think of C as the Euclidean norm, maybe up to some power P. Okay, so given two measures, alpha and beta in P of X, The optimal transport problem is defined as a minimization over this set big pi that I'm going to explain in a second of this quantity here, that is the integral of the cost function with respect to the measures pi. Now, the big pi of alpha beta is the set of all product measures that have alpha and beta as marginals. And normally we refer to such measure in this set as transport plan. Now, for those of you who are not familiar with this problem, just think about it as a way of quantifying the minimum cost that you have to spend in order to move mass from a distribution alpha to a distribution beta. So this is the definition that we give for arbitrary measures. Since we are also going to talk about discrete settings and discrete measure, just to be on the same page of what we mean, let's see also how we write the same optimal transfer problem in this setting. So when we say alpha and beta are finite discrete probability measures, we mean that we can write them as a finite sum of Dirac deltas, of weighted Dirac deltas, where the weights are non-negative and they sum up to 1. So the weights belong to a simplex in some dimension. And the picture that you can have in mind when we talk about discrete measure is something like this. So in the discrete setting, we can rewrite the optimal transfer problem as just a linear programming here, where the set of transport plans now is a special class of matrices, and the integral is replaced by the Frobenius product between a transport plan and a cost matrix. Maybe some of you are not familiar with the general formulation, but you may have seen this discrete formulation here. So what we have seen now is just the definition of the standard optimal transport problem. But what we are going to talk about is actually the entropic regularization of such problems that we just defined. So entropic regularized optimal transport is just defined with a similar minimization problem where we still have these terms that are integral of the cost function, but also where we add a regularizer that is given by the Kullback-Leibler divergence between a transport plan and the product of the marginals that we can weight with a suitable regularization parameter epsilon. This is how you would write the entropic optimal transport in the discrete setting. We just add to the Frobenius product an extra term that is given by the Kullback-Leibler between the transport plan and the product of the marginal, as I just said. Now, as a final definition, we need the following. So when we introduce this Kullback-Leibler divergence in the problem, what happens is that we are introducing a bias. So when we consider entropic optimal transport evaluated at the same measure, this is not zero anymore. And if we want to consider entropic optimal transport as a sort of distance, the fact that it's not zero when we evaluate it at the same measure is something not desirable. So what we can do is that we can use a de-biased formulation of entropic optimal transport that is called synchron divergence. That is defined as follows. So we just like these three terms here where we remove the autocorrelations, and that has, let's say, better properties as a loss function. So the synchron divergence is non-negative. It's indeed zero when we evaluate it at the same measure. And also it preserves the nice convexity properties that also entropic optimal transport has. So in the following, we will use both the entropic optimal transport and the synchron divergence, and the results that we will see hold for both synchron divergence and also just entropic OT trivially. Okay, so now that we have seen the definitions, why are we interested in this entropic regularization in the first place? So let's say when we use optimal transport distances in either machine learning problems or other applied sciences problem, we care about two aspects. So we want to be able to actually compute things in practice. And also we normally deal with just samples from distribution. We don't have access to the actual population measure, and we only deal with a finite amount of samples. So we also want to have a nice statistical behavior. Now, under both these aspects, so the computational one and the statistical one, standard optimal transport distances don't behave well. So in terms of computational cost, algorithms to compute standard optimal transport scale cubically with the number of samples. And on the other hand, if we introduce this entropic regularization and we consider entropic optimal transport, there are more efficient algorithms, such as a well-known synchron algorithm, that allow to compute the entropic OT distances with a cost that is just quadratic in the number of samples. Still, this is not great for very high scale settings, but we are still doing better than standard optimal transport. And the second aspect that I mentioned before is the sample complexity. So if we have a population measure and we have access to a number of samples that are drawn from such measure, the rate of convergence of this empirical measure to the population version under standard optimal transport is 1 over n to the power 1 over d. So that means that in order to have the same representation power, we need to take a number of samples that scale exponentially with the dimension of the space. This phenomenon is known as curse of dimensionality, and it's really something not desirable if we want to just work with samples in high dimensional spaces. Entropic regularization at least mildly mitigates this aspect. So when we introduce entropic regularization in the problem, we have that the rate of convergence of the empirical measure to the population version is 1 over square root of n. So we don't have a dependence on the dimension in the rate anymore. Still, a very bad dependence on the dimension is hidden in the constant, but if we just consider the rate, we don't have a curse of dimensionality anymore. So these two advantages, the computational one and the statistical one, are, let's say, the main benefits of introducing entropic regularization when we want to use it in either machine learning or other applied sciences. But what we are interested here is another class of advantages, which is in terms of regularity, in terms of smoothness of our function. So we are going to see 3 different results. In particular, we want to answer the question, regularity in which sense? And just as a spoiler to motivate why we are interested in this regularity, so in the final part of the talk, the one on machine learning application, we are going to use the regularity that I'm going to present here as a tool to show like theoretical guarantees of the estimator that we are going to see. So let's see what kind of regularity results we can obtain with entropic regularization. The first one is about a Lipschitz continuity property of the gradient of synchron divergence. And we are going to see that in a bit more detail just in a second. The second result is about the sample complexity of the gradients. So how well we can estimate the gradients if we only have access to samples. And then the third result is about high order differentiability of the synchron divergence. And this is just in a restricted setting that we're going to see. So let's start from the Lipschitz continuity of the gradient. To understand the result, we first have to understand who the gradient of synchron divergence is. So when we saw the formulation of optimal transport and entropic optimal transport before, we saw a minimization problem over a certain set of measures. So that one is called primal formulation, but optimal transport and entropic optimal transport also admit a dual formulation that is written as a maximization over pairs of continuous functions of this quantity over here. So we're going to deal with the dual formulation now. And what happens is that the maximizers of this dual formulation are first unique up to a constant and almost everywhere. And also the first order optimality conditions are the one that I've written here. So we know that the optimality condition for this dual problem can be written like this. And in principle, these two equations hold almost everywhere with respect to alpha and beta. So are just true on the support of the two measures. But what happens is that we can use these two formulas in order to extend the maximizers of this dual problem in a canonical way to the whole domain. So this is a subtle technical aspect, but I wanted to stress this anyway, because what happens is that the maximizers of this dual formulation are just called optimal potentials. But in order to obtain the gradients, we have to extend such optimal potentials everywhere on our domain. So just to recap, we have that the gradient of entropic optimal transport is given by the optimal potentials, so the maximizers of the dual formulation that we have just seen, extended on the whole domain X. And we write something like this. Now, the result of the Lipschitz continuity is just literally describing a Lipschitz continuity.
Sorry, Giulia, can I slow you down 1 second? Can you go back? I'm ignorant, I've never seen this. So why do you say it's a gradient?
Sorry?
Because why? So is the gradient in which sense?
So entropic optimal transport is a map from the space P of X times P of X to R, and you want to compute the gradient with respect to the inputs. And what happens is that if you do the computation, you can see them, for example, in some papers by Gabriel Peyret, the gradient of entropic optimal transport is just equal to the solution of the dual problem, extended everywhere.
Okay.
In principle,
okay. So this
the
is
maximum.
A fact.
Yeah, this is a known fact.
Okay,
so
okay. Sorry.
We have this, just that the gradient with respect to our inputs is equal to the optimal potential extended everywhere. And the Lipschitz continuity result says that if we take alpha, alpha prime, and beta prime in P of X, we compute the gradient at alpha and beta. So we obtain a pair of optimal potentials U and V. We compute the gradient at alpha prime and beta prime. So we obtain a pair of optimal potentials U prime and V prime. Then we have the relation that is written in this equation. So if we know that alpha and alpha prime are closed under total variation, and beta and beta prime are closed under total variation as well, then we can conclude that the term on the left-hand side is also small. So the gradient evaluated at alpha prime and beta prime is close to the gradient evaluated at alpha and beta, meaning that if we consider measures that are close to each other, then the gradients of entropic optimal transport will also be close to each other. This is what we mean with Lipschitz continuity of the gradient, and we are going to see an application of this result in the final part of the talk. So this result is going to be useful when we want to perform optimization over the space of measures. So for those of you who are a bit more familiar with the tools that are normally used in optimal transport proofs, so the proof here relies on the Hilbert metric and the relation between the Hilbert metric and the supremum norm, some contraction properties under the Hilbert metric, and then estimates of this quantity here. So these integrals here that I will rewrite in the following slides in this way here that you can see on the right, where I'm basically just using duality between the space of continuous function and the space of finite measures. In particular, just because I'm going to mention this also later on, what we can do is, if we have this duality between C of X and M of X, is that we can find an upper bound that is given by some constant here, and then the total variation, that is the distance that we use on M of X, between beta and beta prime. So remember this part because it's going to be useful also in a second. So these are the ingredients of the proof. And this is the first result that we have in terms of smoothness properties of entropic optimal transport. The second result here, it's similar in spirit, and it's about the sample complexity of the gradients. So as we said at the beginning, when we do machine learning, we don't normally have access to the actual measure, but we can only deal with samples. So what we want to know is the following. If we only have access to empirical measures and we can compute the gradients only on these samples, how far we are from the gradients that we could obtain if we had access to the actual measures alpha and beta. So we have already seen before that just in terms of entropic optimal transport distance, we have that the approximation that we obtain if we use empirical measure with endpoints is of the order 1 over square root of n with high probability. But here we are interested in understanding what kind of approximation we can get in terms of gradients. So how good our estimates of the gradients are. So to answer this question, we can have a look again at the first result that we talked about before on the Lipschitz continuity. So we had something like this. Now, if we knew that the empirical measures alpha n and beta n converged to alpha and beta in total variation with some given rate, we could just upper bound this part here, and we would obtain a sample complexity result of the gradients. However, the problem is that this is not the case. We don't have convergence of the empirical measures to the population measure under total variation because it's a strong norm, so we don't get this kind of convergence. What do we have to do? Then we would like to show a similar result, so a similar result on Lipschitz continuity, but where we can substitute the total variation with a weaker norm, with a norm that under which the empirical measure converge to the population measures. And just to give a sense of why this is true, I'm going to show some of the details here of how we can obtain some sort of replacement of the total variation with a weaker norm. But if you're not familiar with these kind of things, this is just going to be a sort of like technical part that is not functional to the rest of the presentation. So to see some of the details here, we have to consider the following. When we saw the dual formulation, if you remember, we had a maximization over continuous functions. What is true is, and this is a fact that was shown in a paper by Genevieve a couple of years ago. What is true is that the optimal potentials belong not only to the space of continuous function, but also to a Sobolev space, where the parameter that controls the differentiability, so how many weak derivatives we can take, is big enough. So what this is telling us is that the optimal potentials, so the gradients, are not only continuous functions, but they are more regular. And this is what enables us to replace the total variation that we had before with a weaker norm. And now we can see why with more details. So before, when I stated the ingredients of the proof of the Lipschitz continuity, I said, so in this proof, we use some sort of equality like this, and this is going to be useful later. So in the case of total variation, we had just a pairing here between continuous function and measures, and we were using this sort of inequality that allows us to take the total variation here, because the total variation is the metric that we have, on M of x. Now, how can we substitute the total variation with, for example, the maximum mean discrepancy that is weaker? To do that, we have to make this consideration. So for any probability distribution beta in P of x, we can have a representation of such beta in a reproducing kernel hyperspace. So each beta can be represented as an element mu beta in some RKHS H. And this element mu beta is called the mean embedding. And once we have this representation, if we take a function in this RKHS, then the integral of this function in a measure d beta, which is exactly the objects that we were seeing before, can also be written as the inner product in the space H of f and the mean embedding. What is important here is that, of course, the function f that we are integrating belongs to the RKHS. Now, where are we going with this? So because we just saw before that actually the optimal potentials and the gradients are very regular. In particular, they belong to a subwave space with enough differentiability. We have that functions of this type here also belong to the subwave space with enough regularity. And this subwave space is a reproducing kernel Hilbert space. So we are going to be in a similar setting of what we were seeing here. So what we do is that the objects that we were considering before, so the pairing between continuous functions and measures, what we were considering here, is equivalent because we have regularity of these functions to considering the inner product in a reproducing kernel Hilbert space between the same functions and the mean embedding associated to the measures beta and beta prime. And then once we are here, so once we are considering the inner product in H, then we can use something similar again to what we were doing before, some Cauchy-Schwarz, and we have that we consider the norm in H of the difference between the mean embedding. So rather than having the total variation, now we have this norm in H of the difference between the mean embeddings. And this is exactly the maximum mean discrepancy between beta and beta prime. So what this means is that doing this kind of tricks that I just show you, we obtain a Lipschitz continuity result with a weaker norm on the right-hand side. So we have this kind of Lipschitz continuity where we consider the MMD. And now we can say what we were saying at the beginning. So under the MMD, we have that the empirical measures converge to the population measure with a given rate, 1 over square root of n. So we can just use this fact to create an upper bound of this right-hand side, and we obtain the sample complexity of the synchron gradients. So just to wrap up this discussion, here you can see the actual theorem, which is under some assumption, if we have two probability distributions, alpha and beta, and we take, for example, an empirical version of beta with n points that are sampled IID, then the approximation of the gradient scales as 1 over square root of n with a high probability. So we have a result that tells us how good the gradient evaluated in the sample is in terms of approximating the real gradient that we don't have access to. Again, we're going to see how this result can be useful in the final part of the talk. So far we have seen the first result on Lipschitz continuity and this result on the sample complexity. These two results were true for arbitrary measures, while the final one that I'm going to present holds just in a restricted setting. So just when we consider histograms rather than arbitrary distribution. So this final result just says that the entropic optimal transport as a function from the simplex to R is C infinity differentiable in the interior of the domain. So we can take how many derivatives we want with respect to the input arguments. And the proof here is just an application of the implicit function theorem. So it doesn't rely on the kind of tools that I showed before. Okay, so this is the final result in terms of regularity that I wanted to talk about. So we answered the question regularity in which sense. And then we're going to see how this regularity of entropic optimal transport comes at hand when we want to use entropic OT in some machine learning applications. So the applications that I'm going to talk to are the Barycenter problem, and then very briefly, supervised learning setting where we can use entropic optimal transport as a loss function. So just to start with the Barycenters, what we want to compute here are Barycenters of probability measures. Now, if you're not familiar with this, we can just imagine what happens on a Euclidean space. So on RD, we can take a bunch of vectors, and then we can easily compute the arithmetic mean, which is the solution of a minimization problem here. The Barycenter of measures is something very similar. We just have to translate what happens on RD to what happens on the space of probabilities over RD. Again, we have a bunch of input measures, and we want to compute their mean or their Barycenter, solving a similar problem as the one on the left, where we replace the Euclidean norm with a divergence that makes sense on the space of distributions. And in our case, we consider the synchron divergence. So this is a bit of a high-level explanation of what these synchron Barycenters are. Let's just see a bit more formally how we define the problem. So given a set beta 1, beta m of input measures, the Barycenter with respect to synchron divergence is the minimizer, the arc mean of over the space of probabilities of this functional here, which is the Barycenter functional. And it's defined as a sum of synchron divergences, the weighted sum of synchron divergences, where the weights are non-negative and they sum up to 1. So this problem is actually quite popular, and there are a lot of algorithms that were developed to solve these problems here. So in general, there are two classes of methods. The first one is called fixed support methods. And what we do is that we fix a bunch of points a priori, and we assume that our Barycenter is a weighted sum of Dirac deltas centered at such points. So what we only want to compute are the optimal weights. We want to just optimize the Barycenter functional on the weights, and we consider the support points x fixed. In this case, there are several algorithms that one can use. For example, iterative Bregman projections are very efficient. And this kind of setting is also well understood in terms of theoretical guarantees. The second family, on the other hand, is called the free support methods. And what we do here is that we don't fix any support a priori. We also want to compute the support points xi here. And a standard way to do that is to perform alternating minimization and alternating between optimizing the weights and optimizing the allocation points xi. The problem of this approach is that there are no guarantees of convergence to the true Barycenter. And so this is what has motivated us to thinking whether we can find a different approach for computing a free support Barycenter that, however, doesn't rely on alternating minimization. And if for some other approach, we can also show at least partial theoretical guarantees. So the method that we proposed is based on a Frank-Wolf algorithm. And the key features of this method are the fact that there is no alternation in optimizing with respect to the points and with respect to the weights. The Barycenter is just populated using an iterative procedure, and there is no parameter tuning. Now, since we are going to use Frank-Wolf, I wanted to give a very brief recap of the setting that we consider here. So we are going to consider Frank-Wolf algorithm on Banach spaces. This means that we have we need a Banach space W with the topological dual W star. We need a subset of W star that is convex, closed, and bounded. And then, of course, we need a function that we want to minimize that is convex with Lipschitz gradient. And once we have this, we can just use a standard Frank-Wolf algorithm that, at least in the setting that I described, is known to have a convergence rate of 1/k. Now, what we have to check in order to apply Frank-Wolf to our setting is if all these assumptions here are satisfied. So in our setting, we want to minimize the Barycenter functional, right? We have that the dual Banach space that we consider is the space of finite measure equipped with a total variation, such that this space here is Banach. The subset that we consider is the space of probability measures. And here all is good because it's convex, closed, and bounded. The Banach space that we started with is the space of continuous function. And then finally, the function that we want to minimize is the Barycenter functional. And I just recalled the definition here. Now, the last assumption that we had in the previous setting was that the gradient of the function that we want to minimize is Lipschitz. And this is where we use the result that I presented before on the Lipschitz continuity. Because thanks to that result that said the gradient of synchronous divergence is Lipschitz, we can, of course, easily conclude that the gradient of the Barycenter functional is also Lipschitz. And therefore, we are in the set of assumptions that are required by Frank-Wolf algorithm. So we can just apply Frank-Wolf to the Barycenter problem that I described before. And what we have is a method for a free support Barycenter that has convergence guarantees. So in the finite case, what I mean here is that if we assume that our input measures have finite support, then we take alpha k as the case iterate of a Frank-Wolf algorithm applied to the Barycenter problem, then we have that the Barycenter functional at this alpha k minus the minimum is upper bounded by 1 over k. So we have that the algorithm converges and the rate of convergence is 1 over k. Now, here we have this assumption on the input measures. So they need to have finite support. Now, what happens if we are in a setting where the beta j are not finite and where we only have access to the samples? Can we still say something in this case? So the good news is that Frank-Wolf algorithm allows to use approximations of the gradient rather than the real gradient. And this is hidden in the fact that we can have a sort of threshold, a sort of error that we are allowed to make when we compute the iteration of Frank-Wolf algorithm. The point is that, great, we can use approximations of the gradients, but we need to be able to control such approximations. So we need to be able to control how far the gradient of the Barycenter functional evaluated at our samples is from the actual gradient. But here is then where our second result that on the regularity that we saw before, the one on the sample complexity, becomes useful, because we had a result that was indeed dedicated to understanding how far the gradients computed on samples are from the real gradients. And this is exactly what we need in this situation here. So thanks to this result, we can also conclude a convergence guarantee for the general setting. So we have that if the beta hat and beta 1 hat and beta m hat are empirical distributions with n support points, and again, alpha k is the case iterate of a Frank-Wolf algorithm applied to these empirical measures, then we can still say that the Barycenter functional at alpha k minus the minimum is upper bounded by some constant, and then we have the minimum between k and square root of n. So before we just had a rate of convergence of 1 over k, while here we have the minimum between k and square root of n. So this means that we can sort of play a bit between the rate of convergence that we want to achieve and the number of points that we are allowed to sample from our measures. So to be clearer, let's say we can compute just n samples, n equal to k squared samples. So at the iteration k, we can only sample k squared points. Then we will recover the rate of convergence as 1 over k, which is what we also had in the finite setting. On the other hand, if our budget is more limited, so we can only sample k points, then the rate of convergence will become 1 over square root of k. So this is what I meant when I said you can play with the number of points that you can sample at each iteration and the rate of convergence that you want to achieve. So this was the whole theoretical analysis. Just to give a flavor of how the algorithm works in practice, let's see at this example here. So here we want to compute the Barycenter of 30 distributions that are supported on nested ellipses. So each image here is one of the distributions that we use. And if we just run our Frank-Wolf algorithm, this is what we obtain. So at each iteration, we are going to add one more point to the Barycenter. The weights are rescaled according to the Frank-Wolf rule. And what we get is that at convergence, our Barycenter is also supported on two nested ellipses. And this is because of the nice geometric properties of optimal transport distances. Okay, so this is what I wanted to say on this unsupervised problem. So when computing barycenters of measure, the final application that I wanted to briefly talk about is a supervised learning setting. And here I'm going to be more high level and I'm not going to go into details. So the learning problem that we consider is a standard supervised learning problem. So we have an input space, we have an output space that for us is the space of histograms. So just a simplex in some dimension. Then of course we have an unknown probability measure on input-output space that can only be accessed through a finite number of samples. Then we need a loss function that for us is a synchron divergence or entropic optimal transport. And our goal is the following. So remembering that the expected risk of a relation between input and output is defined like this, we want to be able to find a good approximation, Fn, of the minimizer F star of the expected risk, only using our training set. And when I say good approximation, I mean that we want to be able to say something on the statistical properties of our estimator Fn. So to give a brief motivation on this setting here, where we consider entropic optimal transport as a loss function, this was first done in a paper in 2015 by Frogner and collaborators that is called Learning with Wasserstein Laws. And in their case, they were considering a setting similar to ours, but the entropic regularization was just used as a computational trick. And in this paper, they didn't study the statistical properties of the estimator that you can derive. So this is what motivated our work. And in order to get this sort of statistical analysis of the estimator, we proceeded in this way. So we interpreted the problem that I described before as a problem with the structured outputs. So our output space is the space of histograms, so it's a simplex, and which we just interpret it as a space with structured outputs. This is just to say that we want to use, let's say, an approach that is standard for structure prediction problems, and that relies on surrogate framework. So the intuition behind surrogate framework is the following. We have some output space that for us is the simplex. Then we have an encoding function that brings us from this output space to a surrogate space that is normally Hilbert space. Then we solve our problem in this surrogate level, and we obtain a surrogate estimator. And then what we do is that we have also a decoding function that brings us back from the surrogate level to the original problem. And that brings our surrogate estimator into an estimator for the original problem. Now, in order for this procedure to be valid, we need to know that if we have a good estimator for the surrogate problem and we use this decoding, then we are going to obtain a good estimator for the original problem. So we need some sort of coherence of all this procedure here. And this is where we use our final results on the regularity properties that I showed before, the one on high order differentiability. Because what happens is that because our synchron divergence is very regular, since we have this high order smoothness, then one can show that the encoding, surrogate, and decoding procedure that I described is a valid procedure, meaning that it leads to having a consistent estimator with provable learning rates. So if we use this kind of surrogate approach, what we have is that we can design a consistent estimator with learning rates for learning with synchron divergence. And this is something that was not explored in the first paper, in the paper on supervised learning with optimal transport loss that I showed before. Okay, so to wrap it up, we showed that the entropic regularization leads to a range of smoothness properties. In particular, we saw the Lipschitz continuity of the gradient, the sample complexity of the gradient, and also a high order differentiability of entropic optimal transport on the simplex. And then we used such smoothness properties to show theoretical guarantees in two different settings. The first one was the synchronous Barycenter problem with free support, where we were using Frank-Wolf algorithm. And the second one is a supervised learning setting where we use synchron loss or entropic optimal transport as a loss function. So I guess this is everything I wanted to say, and thank you for the attention.
Thank you. Thank you very much, Giulia. So, do you have any questions?
I have some questions.
Two. Okay, so
Cesare first.
Cesare first.
You can do one, you, and me again.
Flick-flock, you go first.
The first one is just a curiosity. Can you say something when you don't regularize about the gradient, or if you send epsilon to 0?
Okay, so if you send epsilon to 0, you're not going to get a good results because the constants that depend on epsilon will explode. So here, to have an easier notation, I was just saying something on these lines. So here we are hiding the constants. However, you can compute the constants explicitly. So you have an explicit dependence on epsilon. If you send it to 0, the constants are going to explode. So if you want to say something on the unregularized setting, you probably have to do something different. So not going through the entropic regularization. And what I can say here is that in order to develop all the proof here, we were using these aspects. So we were using that the optimal potentials of the regularized problem are not only continuous, but they also have a higher regularity. And I think if you consider the standard optimal transport problem, then this is not true anymore, or at least it's way harder to understand the cases where you have some regularity of the potentials.
Okay, thank you. And even if you don't regularize, the expression for the gradient is the same, is UV.
So if you don't regularize, yeah,
you are still differentiable.
No, well, you don't know much on the regularity of the optimal potentials when you don't regularize. So the dual problem looks similar. You just don't have this, and you have a hard constraint on the set where you maximize. But then I think it's way harder to say something on the regularity of the potentials.
Okay, thank you.
Lorenzo?
Yeah, so I was curious. So the smoothness, so the regularity index of the Sobolev space where you can embed the potentials, that comes straight from the assumption you have on the cost function, right? So you assume that the function is S-time differentiable and then tells you how much smoothness you can have on the potential. But then I was a bit surprised that, I can take S arbitrarily high or arbitrarily close to the half, and the results seem to be always the same, which is counterintuitive. For example, even when you look at MMD, so I was wondering how come that nothing depends on the smoothness, nothing improves it. If I take S, which is 3 gazillions or d half, it's always the same.
So I think you have some dependence on S, always in terms of constants.
Okay.
And what I also wanted to say, I mean, here I didn't mention it. So in our results, as you said, we assume our cost function to be smooth enough to be S plus 1 times differentiable. However, there is another paper that was published after this, where they improved this aspect. So I think they can get a similar results on the ellipsis continuity on the gradient, but rather than requiring the cost function to be s plus 1 times differentiable, I think they have something less strict. It's a paper that is called synchron barycenters via functional gradient.
Okay.
So this assumption is probably not necessary.
Okay. Yeah. Okay. Okay. So I'll look it up, because then I'll be curious to see where the S is coming from, if you don't assume that. But and the other question is, I wonder if you can flip the reasoning and say, so right now, basically, to be sure that you can define a divergence or over all possible distribution, you need this smoothness condition, and then this define a reproducing kernel space, and then you have MMD. I wonder if you could get some blessing if you say, okay, I want to restrict myself to a smaller class of distribution that can be represented by a simpler kernel. Because again, here the kernel is dropping from nowhere. So I could say, I don't know. I mean, for example, the guess on kernel is enough. So in some sense, my distribution are well described by the space of function which is analytic. And again, I wonder in that case if you would restrict the space of distribution that are well described by an MMD defined by a kernel of my choice, I could get something any better. Is there any results in this sense where you basically say, okay, I want to do everything you said on a smaller set of distribution which are nicer?
I think the issue might be that you still have to understand where the potentials belong. Because if you take, if you just say that the potentials are in the Hilbert space, the sublevy space that I said before, then you would still have to deal with that space in order to be able to write something like this.
The hope is that maybe there will be analytic functions rather than just in W2 S2.
We tried a bit in that direction. So we were interested in exactly this aspect, in trying to see whether restricting the class of functions, we can say something more on the regularity of the potentials. We wanted to do that as an extension of these results. And I mean, we didn't manage to do that. We didn't look into it too much. And I'm not sure if there are papers that do that. I don't think so, but it's a question that we were also interested in. Because I think it would be nice to know whether, for example, all the measures admit density and this density is smooth. What can you say, even in terms of other properties like sample complexity and these other things?
Yeah, exactly. Yeah, that would be the simple case to look at. Yes. Yeah. Okay. Thanks.
Are there other questions? Otherwise, I have also a couple of questions. So one maybe is more of a high-level observation about what you were saying now about the smoothness of the potentials when you have smoothness of mu, which so I think it might depend on some interpretation as Monge-Ampere equation, because if in the non-entropic case, if the measures are smooth and the cost is quadratic, then you have you have as smooth as you want U. But as long as you don't have quadratic or something like that, then everything breaks down. And so if you need some higher regularity which goes beyond the regularity of the cost or something like that, I fear that one should play with some kind of Monge-Ampere analog in this case, something like that. And so, but the questions I had is that, so it seems that, so one question is related to the Cesare one. So the constant depends on epsilon, right? And it seems that depends like in exponential of constant over epsilon.
Yeah.
So it really blows up. So do you expect that the real constant in terms of epsilon is, so it depends more mildly in epsilon, so like 1 over epsilon or 1 over epsilon to the d or something like that?
Yes, I expect that, but I don't know how to prove it. So in the sample complexity result, if you look at paper by Genevieve, where they first showed that the sample complexity doesn't suffer from curse of dimensionality. In that case, they also have like horrible constants that depend as epsilon of something, exponential of something minus epsilon and so on. But in a paper that was published later on, the one by Niles Swede and Gonzalo Mena, they showed that actually you don't have such a horrible constant, and you can obtain a constant that is polynomial in 1 over epsilon. And I was hoping to do something similar here as well. But with the kind of proof that we have here, that is like uses the Hilbert metric, the GID problems, we were not able to remove the exponential dependence in the constants. But yeah, this is something that actually I've been thinking about quite a lot, because I was really hoping to improve that part. But with the present approach, I don't think it's possible, and I didn't find like another approach that would lead to better results.
Okay. Because
but I think it should be possible.
Because then it would lead to better constants also in the convergence of Frank-Wolf algorithm, etc.
Yes,
so
yes,
it's
important.
So I think that maybe you see a better convergence than expected in numerical.
Yeah, numerically you don't see this horrible dependence on the regularization, because in the experiments we used a regularization that is like quite small in order to get nice results, and you don't see this kind of behaviors. But in the proofs, yeah, we were not able to remove this dependence.
And so the other questions, the other question was about the last example, so the one with the supervised learning. So is that like, so I think it can be seen as a generalized Barycenter. So really the problem of supervised learning, right? So the minimizing the integral of S epsilon of the integral of the divergence. So it can be seen as a general mean, yes, so a mean of some kind that you are trying to do. And so my question is, so does your proof in some sense provide some convergence of discrete discrete Barycenter to this kind of continuum Barycenter, where you have not a fixed number of marginals, but maybe a plethora of marginals, continuum type. I don't know if it's clear, the question.
No, say it again. You want to
No.
say whether we converge in terms of just generalized Barycenters to these objects here? Yeah,
I mean, is this so this? No, okay. Maybe I'm horribly wrong, and this is expected risk of a function. So you are trying to look for a function. Okay, no.
But what you're saying is kind of related to the kind of estimators that we get, that I didn't put here. Like here, there are no details. But if you look at this paper, it's called like a consistent regularization approach for structure prediction, and this is the setting that we're using here. You see that the estimator Fn that you get is actually some sort of generalized Barycenter. And what I mean with generalized is that the weights can also be negative, because they're obtained using solving the surrogate problem, which is just a kernel ridge regression. So you know that at the limit, the weights will have to approximate a distribution, so they won't be negative anymore. But when you solve the problem with just a fixed training set, you get an estimator here that is the arc mean that you obtain via the decoding of a sum of weighted synchro divergences. And the weights can be also negative. That's why I say generalized. And then, in practice, you could, there are different tricks that you can use. Either rather than using kernel ridge regression in the surrogate, you use other approaches like Nadaraya Watson that will give you positive weights. Or you could also say, since the bigger the number of points is, the less negative weights I will have. You could also set some threshold and just, remove some of the negative weights, and you can just use Barycenter algorithms.
Okay.
So yeah, what you're saying is actually related to the estimator here that we get.
Mm-hmm. Okay. Thank you very much. So are there other questions?
I have the last one.
Yes,
very short. It's a practical one about the linear minimization oracle of Frank Wolf. How do you solve it? I mean, you have to compute the gradient, so you have to solve a dual regularized problem. And then?
Yeah, so you have to compute the gradient of the Barycenter functional, which is just given by the potentials, so that's can be computed. And then in principle here, you would still have a minimization over a set of probability measures, right? Because T is our probability measure space. But sorry, what happens is that since here, you're minimizing a function that has a specific form, so it's of this type here, then you already know that the minimizer are going to be extreme points of your domain. And the extreme points of the set of probability measures are Dirac deltas. So that means that you are computing this quantity where the right-hand side, let's say, is just with Dirac deltas. So this just amounts of minimizing a function because you evaluate the gradient on Dirac deltas. And then here you still have like other issues. So the functions that you want to minimize as an inner step is not necessarily convex. So you also have to come up with a good way of finding the minimizers for the inner step. In the experiments, we never observed like a bad non-convexity, but also our experiments were in low dimension, and I mean, maybe we didn't fully explore the set of possibilities. I think in principle here, you could have like bad behaviors of the function in the interstep, even though we didn't observe them. So you could either use some, I don't know, multiple starting points and then just pick the best solution that you get, or do something for non-convex optimization. You have smoothness, but you don't have convexity here.
Thank you very much. Thank you.
Welcome.
Okay. So thank you again to Giulia. And